Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course. States of matter. Today we begin with lecture 2 from the course, but make sure you watch the previous lecture before viewing this one. So the last lecture, this was an introductory lecture wherein we learned that we have at the ordinary temperature and pressure conditions three states of matter, that is the solids, the liquids and the gases. And this classification of matter into solid, liquid and gases is based upon the intermolecular forces. So we in this lecture would be having a detailed discussion on these intermolecular forces. I gave you a brief introduction in the last lecture as well, but we will be talking about this in detail in this lecture because this is a very important thing that you have to understand. So intermolecular forces, as I was discussing in the last lecture, these are also called as van der Waals forces behind the name of the Dutch chemist van der Waals, who first of all studied them. How do we define them? Intermolecular. So this means what? Among the molecules. So we define these forces to be the forces present among the various molecules of a substance. But in actual seeing, these are not just present among the various molecules. These can be present among molecules. It can be present among even atoms as well. And it will be seen even between and molecule and ion also. Okay, so we will be discussing in detail about this. But when I talk about atoms, let me tell you one thing that we've already studied before. While we were discussing the course of the periodic classification of elements, there we studied about the atomic radii. In that we studied that there are three types of atomic radii that we study: the covalent radii, the metallic radii and the van der Waals radii. So that was the first time you heard the name van der Waals, right? And what did we talk about there? We talked about that the noble gases, they are not chemically reactive, so these are not forming bonds, so there will be no covalent bonds, no metallic bonds. So these atoms, they will be experiencing very weak forces, and those weak forces we call them as the van der Waals forces, right? I hope you remember. So this is these forces that we are talking over here. These are very weak forces which may be present among the atoms, ions, molecules. Okay, so we will be discussing about all of this in detail. Now, the next thing that you have to understand is that these intermolecular forces, they are pure electrostatic forces. What do we mean by electrostatic forces? That we will be seeing in the molecules that there will be the development of charges, right? So when we talk about electrostatic, it is related to charges. And you have heard this electrostatic force as well. When did you hear it? When we were talking about ions. The ions, the oppositely charged ions, when they are attracting each other in the formation of the ionic bond, what were the forces of attraction? They were the electrostatic forces of attraction. So here these are pure electrostatic forces, but these are not electrostatic forces of attraction that were present among the ions, the oppositely charged ions. For example, when we consider the formation of a NaCl, bond over there, the ionic compound, sodium chloride, sodium ions, they are positively charged, the chloride ions, they are negatively charged, they experience an attraction towards each other, which we call as the electrostatic force of attraction or the ionic bond. So these are pure electrostatic forces, but they are not proper bonds. So this is not an ionic bond. This is not even a covalent bond. So the atoms, we say that there can be the intermolecular forces can be between atoms as well, but then it is not those atoms which are sharing their electrons. It is not the covalent bond that they are forming which we categorize into the intermolecular forces. Okay, so these are going to be weak forces when we compare them to the ionic and the covalent bonds. So ionic and covalent bonds, they are chemical bonds, and these intermolecular forces, they are physical bonds, they are weak forces that we will be studying. The next thing we have over here is that we have two types of intermolecular forces. There will be attractive forces, there will be repulsive forces. When two molecules, they come close to each other, they will be experiencing an attraction to each other. They will be experiencing a repulsion also. And this is all that we are discussing in this lecture, the attractive forces as well as the repulsive forces. And it will be the cumulative effect of these forces that we get the three states of matter, that is the solids, the liquids and the gases. Right. So first of all, we will be discussing in detail the various types of attractive forces, because this is something that is very important, and then I will be briefly telling you about the repulsive forces as well. So the various types of intermolecular forces of attraction that we have are the dispersion forces, which we also call as the London forces, then the dipole-dipole forces, the dipole-induced dipole forces, the ion-dipole interactions, and the hydrogen bond. So we will be discussing them in detail one by one. So the first type of intermolecular forces are the dispersion forces or the London forces, and these are called as London forces because they were studied for the first time by the German physicist Fritz London. Now please do not confuse this. All the five types that I have told you, all these are intermolecular forces, so all of them they are called as van der Waals forces, but this one type that we will be discussing now, these are called as the London forces, a special name for these intermolecular forces because they were studied by the German physicist Fritz London. Otherwise, this is also an intermolecular force. This is also a van der Waals force. Okay. Now, how do we understand what are these forces? Let us see one diagram over here. We have two atoms, atom A and atom B. In the case of atom, there is a symmetrical distribution of the electron cloud around the nucleus, right? So in another atom, so there will be also a symmetrical distribution of electron cloud. So these atoms, when they are not having a transfer of electrons from one atom A to the atom B, there is not the formation of the ionic bond. When these two atoms, they are not sharing their electrons, they are not forming covalent bonds. So those cases, these atoms, for example, in the case of the noble gases, where there is no chemical interaction taking place between the atoms, there is no actual transfer of electrons or sharing of electrons, these two atoms, they are experiencing some forces, and these forces are the dispersion forces. Okay, and this can also be seen among the non-polar molecules also. Why in the non-polar molecules? Because in the non-polar molecules, for example, the H2 molecule, the O2 molecule, there also there will be a symmetrical distribution of the electron cloud. Had these been polar molecules like the HF molecule, there was a electronegativity difference between a hydrogen and fluorine atom. So there is a tendency of the electrons to move more closer towards the fluorine atom when the HF molecule is formed. So there we see a charge separation, we see a dipole being created, and such molecules we call as the polar molecules. So there is not going to be a symmetrical distribution of electron cloud in the polar molecules. But when we talk about the non-polar molecules, there is going to be a symmetrical distribution of the electron cloud. And between two non-polar molecules also we will be seeing these dispersion forces coming into play. So the dispersion forces we will be seeing in those atoms and molecules where there is a symmetrical distribution of the electron cloud. These is no charge separation, no dipoles present. Right? First thing, this is clear to you people. Now what happens over here is that at one instant of time, what happens is that the electrons, they are constantly moving around the nucleus in a three-dimensional space which we call as an orbital. So this is a three-dimensional space where the electrons, they are moving. At one instant, just think, at one instant, it is a possibility that the electrons, rather than being symmetrically distributed around the nucleus, there is an unsymmetrical distribution. The electrons, they move towards one side, and that region will become more electron rich and the other region would become less electron rich. In that case, what will be the structure of that atom or the molecule? You can understand this. So this is the nucleus present in the center. There is increased electron density on this side and less electron density on this side of the atom or the non-polar molecule now. Okay, so I hope you can understand this. I do not have to repeat it again and again. It can be an atom, it can be a non-polar molecule. So what has happened is that any instant of time, a dipole has been created in this atom, right? How has it been created? The electrons, they have slightly shifted towards this side. So this is an electron rich area, this is an electron devoid area or a less electron rich area. Okay, so we are having electron density here means that there will be a partial negative charge on this side, a partial positive charge on this side. So this will result in the creation of a dipole which will be directed in this direction. Fine, and this is what we call as an instantaneous dipole. At any instant of time, a dipole has been created. This is not a permanent dipole. This is just a temporary dipole at any instant of time which has happened. Now what happens over here is, if I just keep this picture over here, so there was an atom A, there was an atom B. Under the influence of this instantaneous dipole, this atom B is also going to be affected. It will not remain unaffected. What will happen? Because there is an increased electron density in this region, the electrons which are going to be present near to this side. So this was the side where now we have an electron density increased now. So this region over here, there is again electrons present. Here we have more electrons now present. So electrons, they will be repelling each other. And when they will repel each other, what will happen? The electrons, they will start going towards this side. And as a result, what we will be seeing is, now what we will be seeing as a result over here is that the electrons, they have moved towards this side. So there is an electron density increase over this side, and now we have less of electron density on this side. So what has happened again? Now this atom B has also a dipole directed towards this direction. Atom A's dipole directed towards this direction. Atom B directed towards this direction. This was an instantaneous dipole, and atom B, this has an induced dipole. It did not have any dipole, but under the influence of the dipole of atom A, a dipole has been induced in this atom. Right? I hope this is clear. So what has happened? We have now a partial positive charge, a partial negative charge, a partial positive charge, a partial negative charge. Next molecule or atom also going to be there, that will also be having a partial positive charge, and the other side the partial negative charge. So in this way we have a partial positive, partial negative, partial positive. So partial negative, partial positive, they are going to attract each other. This attraction, this is a weak attraction, this is a temporary attraction, and this attraction we call as the dispersion force. Right? I hope this is clear. This is an attraction between an instantaneous dipole and an induced dipole. So we can also call it as an instantaneous dipole, induced dipole attraction, the dispersion force or the London force. I hope all this is clear to you people. We had two atoms which were having a symmetrical distribution of the electron cloud. At one moment of time, an instantaneous dipole developed in this atom A. As a result, atom B also got an induced dipole, and now they are attracting each other. Right? So this is a weak force. Now let us read these lines. You will be able to have a better picture again. So this is a temporary dipole. It was not present in the atom or the molecule. So this is a temporary dipole which has developed in a neutral atom and the molecule, possessing symmetrical electron distribution due to a momentary, any moment electronic charge distribution in one of the atoms, say A, becoming unsymmetrical. And this resulted in the development of an instantaneous transient dipole on atom B. This distorts the electron density of the other atom B close to it, and here we have an induced dipole in atom B. Perfect. Now, this can be the reverse direction also, that this atom A, this got a instantaneous dipole development, but now the electron density is more towards this side. So the only difference would be that the direction of the dipole will be different, but otherwise the atom A has an instantaneous dipole in this direction, and atom B will also be having the direction of the dipole just like the atom A. Okay. Now these dipoles, they are temporary dipoles, as I told you. So please do remember, these are not permanent dipoles, these are temporary dipoles, and these temporary dipoles, they are attracting each other, and these are what we calling as the dispersion forces. The next thing is that these forces, they are always attractive forces, they are never going to be repulsive forces. And when there are going to be forces of attraction, there is going to be involved some energy also. This energy we call as the interaction energy, and the interaction energy, this is inversely proportional to the sixth power of the r, where r is the distance between the two interacting molecules. So we have two interacting molecules, there is some distance between them. The sixth power of r is going to give us the relationship to the interaction energy. So this is something that you have to remember. We do not have to discuss more about it. This is all that you have to remember, that the interaction energy in case of the dispersion forces, this is going to be inversely proportional to the sixth power of the distance between the two interacting molecules or the atoms, whatever we are taking into consideration. The next thing is that these forces, they will be acting only at short distances. When the atoms or the molecules, they are going to be far away from each other, these forces, they will not come into play. So the distance is going to be approximately in the order of 500 picometer. And when these forces, they are acting only at short distances, what you can understand is that, for example, we have gases. In the gases, the molecules or the atoms, they are going to be far away from each other, right? But when we are going to decrease the temperature of the gases, the gas molecules or the atoms, they are going to come close to each other. At that moment, when they are coming close to each other, these forces, they will come into play, and this is going to result in the condensation of the gases. So the London forces, they are responsible for the condensation of gases. Please do remember, very important. And the other thing is the magnitude of these forces. So the magnitude is going to depend upon the polarizability of the particle. Now what do we mean by polarizability? What we have studied is that an atom or a molecule will be polarizable when the size of that atom or molecule is going to be more, which means that the atom's nucleus and the electrons, it is the nucleus is attracting, they are far away from each other, so they are under a weaker pull, so they can be attracted by the nucleus of the other atom or the molecule. So more is going to be the size, more is going to be the polarizability, more is going to be the London forces that are going to be present. And this is something that we have already discussed while we were discussing the Fajan's rule. So if you do not remember, please do go and have a look at the lecture on the Fajan's rule, which is available at our channel. Now, so this is what we have in the dispersion forces. The dispersion forces, it is an attractive force in an instantaneous dipole and an induced dipole. Now let us see the next one. So the next we have is the dipole-dipole forces, also called as the Keeson forces. And now these are going to be very easy for you to understand once we have studied the dispersion forces, because everything is going to be just the same way, just the type is going to be different. Okay, so as the name suggests, it is going to be dipole-dipole forces, the forces acting between the molecules possessing permanent dipole. And which are the molecules which possess permanent dipole? These are the polar molecules. So these are the forces of attraction between the polar molecules. So for example, we have the HF molecule. So you know the HF molecule, this is a polar molecule. The fluorine atom is more electronegative than the hydrogen atom. So when a covalent bond is formed between the hydrogen and fluorine atom, the electron pair is going to be pulled towards the fluorine, and so there will be more electron density towards fluorine, a less electron density towards hydrogen. So we say there is a charge separation that has been created, a dipole that has been created. There is a partial negative charge on the fluorine and there is a partial positive charge on the hydrogen end. And then one more important thing that you have to always remember, that this is a partial charge that is present on the fluorine end and a partial positive charge on the hydrogen. It is not a complete charge. So the complete charge, when there is a complete transfer of one electron, say from hydrogen to fluorine, had it that been there, the charge would have been 1.6 into 10 power minus 19 coulomb. We have 1 unit charge equal to 1.6 into 10 power minus 19 coulomb, that is the charge on one electron. And the charge on the electron, that is the least known charge to us. That is why we call that as 1 unit charge. Okay, so here the complete transfer of electrons is not taking place, so the charge is less than 1 unit charge always. That is why we call it as a partial charge. Okay, now what happens when one polar molecule comes in contact with another polar molecule? So we will be seeing that the fluorine end, this is having a partial negative charge, the hydrogen end is having a partial positive charge. So when these two molecules, they approximate each other, one having a partial negative, one having a partial positive charge, they are going to feel an attraction towards each other. So this attraction between these two molecules is called as the dipole-dipole force of attraction. I hope this is clear. Now the other thing is that the fluorine ends, they can also approximate each other. In that case, it is going to be a repulsion. But what are we talking here about? Only the attraction part. So please do understand that when the fluorine end and the hydrogen end, they will be approximating each other, the force of attraction they are going to feel towards each other, that is called as the dipole-dipole force. The other thing you have to remember is that this force is not a very strong force again. This is just 1% as strong as a covalent bond. So this force between the hydrogen and the fluorine atom, when they were forming a chemical bond, a covalent bond formed by the sharing of electrons, this is a strong force of attraction, but here this force is a weak force. Similarly, the other thing that you have to remember, that these forces, they are going to be stronger than the London forces. In the London forces, it was an instantaneous dipole. It was in the molecule first of all, right? And then that instantaneous dipole had introduced a induced dipole in the other molecule. But here we already have dipoles in the molecule itself. So these forces, they are going to be definitely far strong than the London forces, but they will be weaker than the ion-ion interaction, that is in the case of the ionic bond. So the ionic bond, there is a complete transfer of electrons, so these are going to be strong electrostatic forces of attraction. The covalent bonds are also going to be strong. Then we will be having these dipole-dipole forces, and then the London forces are going to be the least from all these four. Okay, I hope this is clear. So the next we have is the interaction energy for the dipole-dipole interactions. So here you have to remember two things, that in case of the dipole-dipole interactions between the stationary polar molecules, as in the case of the solids, the interaction energy is going to be inversely proportional to RQ, whereas in case of the rotating polar molecules, this energy would be inversely proportional to R to the power 6. Now, this is equal to the dispersion force also that we studied, that in case of the dispersion forces, the interaction energy was inversely proportional to R to the power 6. Whereas when these are close, the forces of attraction are going to be more. So we will be seeing that in case of the stationary polar molecules, this energy is more than the dispersion forces as well as the dipole-dipole forces for the rotating molecules. It will be inversely proportional to RQ. Okay, so when the molecules they are stationary, there are going to be more forces. When the molecules they are going to be rotating, they are going to be moving, the interaction energy would decrease. The next thing over here you have to remember is that when these polar molecules they are interacting, there is going to be a dipole-dipole interaction, but the London forces are also present. Okay, so the intermolecular forces that we will be seeing in the polar molecules, this will be a cumulative effect of the dipole-dipole forces as well as the London forces. So in the case of the in the case of the polar molecules, the intermolecular forces are going to be strong. They are not going to be as strong as the covalent bonds, the ionic bonds, but definitely they are going to be strong because of the cumulative effect of two forces. Fine. The next thing that you have to remember, a very important thing that you have to remember, that when the dipole moment is high, the polarity of the molecule is going to be high. Therefore, the interaction energy, the forces the molecules they are going to feel towards each other, that is going to be high. So, higher is the interaction energy and higher is going to be the melting and the boiling point of the compound. So, to melt a solid, we have to convert it into a liquid. So in that case, the molecules they are moving farther away from each other. Similarly, when we convert a liquid into a gas, we have the boiling point in that case. So the boiling point is going to be high when we have to move the molecules farther away from each other, and the forces between them they are high. If the forces are going to be high, there is going to be a difficulty in separation. We have to spend more energy in the separation of the molecules, and in that case the melting and the boiling points they are going to be high. So in case of the polar molecules as compared to the non-polar molecules, the melting and the boiling points they are going to be high. For example, if you see over here, we have a slightly polar molecule NO. So there is a electronegativity difference between nitrogen and oxygen, and there is going to be a slight polarity in the molecule. So in this molecule, if you see the boiling point, this is minus 151 degrees Celsius as compared to the non-polar N2 where the boiling point is minus 196 degrees Celsius, and oxygen the boiling point is minus 183 degrees Celsius. So in case of nitrogen and oxygen, which are non-polar molecules, the boiling points they are lower as compared to the NO molecule, which was a polar molecule. Okay, so I hope you can remember this. This is something that is very important, that because of the dipole-dipole interaction, we have the polar molecules having higher boiling points and melting points. So similarly, if you see the water molecule and the ammonia molecule. So water, this has molecular weight 18. Ammonia, this has molecular weight 70. One thing that you remember over here, that the boiling points they increase, the melting points they increase with increase in the molecular mass. More is going to be the molecular mass, more is going to be the boiling point. But when you see this water molecule and ammonia molecule, they have almost similar molecular weights, right? But here in the case of water, the dipole is going to be more. We have the dipole moment to be 1.85 dpi, whereas in the case of the ammonia molecule, the dipole moment is 1.49 dpi. So water molecule, this has a higher dipole moment. So here we will be having more dipole-dipole interactions. Then therefore the molecules they will be coming closer to each other. The water is existing as a liquid and the ammonia is existing as a gas at the same temperatures. Okay. So the attractive forces in the case of the water molecules, we are seeing they are more pronounced, and they will be more pronounced than the non-polar molecules definitely. Okay, so I hope you will remember these things. These are very important. The hydrogen bonds now. The hydrogen bonds which are found in the polar molecules like HF, water, ammonia, these are a special case of dipole-dipole interactions. We will be just now talking about in the coming up slides. So we will be talking more about it. Okay. So the next we have is the ion-dipole interactions, and I hope you can understand now them very well yourself also. These are going to be the interactions which are going to be present between the ions and the polar molecules. So the ion, either it is a cation or an anion, this will be attracting the oppositely charged end of the polar molecule. One thing that you have to remember over here is that these ion dipole interactions, they will be stronger between a cation and a polar molecule than between an anion and a polar molecule, because the charge density on the cation, this is greater than on an anion due to the small size of the cation. Okay, now let us see one example of this. So we have the hydration of the ions, and this is something that we have already studied while we were discussing the course on chemical bonding, when we were talking about hydration energy. So when there is a hydration of the ions, for example, we have an aqueous solution of sodium chloride. So we have put the common salt, sodium chloride in water. What is going to happen? The polar water molecules, they are going to get attracted towards the sodium ions, the chloride ions. There are going to be ion-dipole interactions between them. The water molecules, they will be acting as therefore a dielectric. They will be surrounding the sodium ions, the chloride ions. They will not allow them to interact with each other. Right? So this is how the dissolution of sodium chloride happens in case of water. You can watch that lecture. There are whole diagrams for this given very beautifully, so you will be understanding the whole concept better if you have not watched that lecture till now. So the hydration of ions is one example of the ion dipole interactions. In the case of carbon tetrachloride, this is non-polar, so this cannot dissolve sodium chloride into it. So this being non-polar, this lacks the ability, and therefore carbon tetrachloride is a poor solvent for ionic compounds. Fine. Next we have is two forces that I am discussing together over here. We have the dipole-induced dipole forces and the ion-induced dipole interactions. So I hope you can understand that there is one polar molecule and one non-polar molecule. There is one ion and one non-polar molecule. The attractive forces between them, these are going to be categorized as dipole-induced dipole forces and ion-induced dipole forces, and these are also called as the Debye forces. So just let me talk about first one, that is the dipole-induced dipole. So what is going to happen? We will be having one polar molecule, the other is going to be a non-polar molecule. So we have a HF molecule, a oxygen molecule over here. So the fluorine, and this is a partial negative. So what will happen to this end of this non-polar molecule? This will develop a partial positive charge. So this will be the induced dipole over here. This would develop a partial negative charge. So what is going to be the direction of the dipole in this? It is going to be again same way as we have for the HF molecule, right? So if this would have been on this side, we would have seen the end that is going to be towards hydrogen, it would have been a partial negative charge, and the opposite end, that would have been a partial positive charge. So that is, I think, now very clear to you people. You can understand this very well. So here the interaction energy is going to be again similar to the dispersion forces. So this is going to be inversely proportional to r to the power 6. And the induced dipole moment, this very importantly remember, this will depend upon the dipole moment of the permanent molecule. More is going to be the dipole moment of the permanent molecule, more is going to be this force. This will also depend upon the polarizability of the neutral molecule, how well it can polarize itself. So the larger molecules or the atoms, they can be easy polarized, high polarizability, therefore this would increase the strength of the attractive interactions. So in case of the dipole-induced dipole forces, the factors that are going to be important are going to be how strong is the permanent dipole, how much is the polarity of this molecule, and how easily this molecule can polarize itself. Okay, the cumulative effect of the dispersion forces and the dipole-induced dipole interactions are going to be always present over here as well. Okay, so we will be seeing a cumulative effect of two forces again over here, but these forces, they will be weaker than the dipole-dipole interactions, right? So this is a dipole and a induced dipole. The dipole-dipole interactions, they have to be at least stronger than them. I hope you can understand. And these are going to be stronger than the dispersion forces. So you can build up a order in your own mind also, that how is going to be the strength of these forces. So the next type of intermolecular force that we study, and this is the last one that we will be studying, this is the hydrogen bond. And as I told you previously also, this is a special case of dipole-dipole interaction. So what is a dipole-dipole interaction? The interaction between the two polar molecules, we call it as a dipole-dipole interaction. And there also what we studied, the example was of the HF molecules, right? So HF molecule, these are polar. So when they will be attracting each other, the force of attraction between them, this is a dipole-dipole interaction. There is a partial negative charge on fluorine, there's a partial positive charge on hydrogen. So the next molecule also partial positive charge on hydrogen. So these two, they are going to attract each other. This is a dipole-dipole interaction. Now why we call this as a bond? That is what we have to understand over here. We are calling this dipole-dipole interaction between the two HF molecules to be a hydrogen bond. Why we call it as a bond? That is something that we have to understand, right? So we have the fluorine atom of the molecule. This is the most electronegative element in the periodic table. You have studied this. Similarly, if you look at hydrogen, this is the most electropositive non-metal that we have, right? So the most electropositive non-metal and the most electronegative element of the periodic table, when they are going to form a polar bond, that means that there is going to be a maximum electron density towards fluorine. So the partial negative charge on fluorine is going to be maximum. The partial positive charge on hydrogen, that is going to be the maximum. So as a result, when the next molecule partial positive charge is going to be attracted towards the partial negative charge of fluorine, this attractive force is going to be really very strong. And this is so strong that we call it as a bond, right? So now this is what we have as the hydrogen bond. We will be talking in detail about this bond because this is very important for us. We will be having so many examples of hydrogen bonding when we will be studying inorganic chemistry and organic chemistry. So I will be putting up a complete lecture on hydrogen bonding, which will be the next lecture. Okay, so just briefly telling you over here, the hydrogen bond, the bond energy is 10 to 100 kilojoule per mole. This influences the structure and the properties of many compounds like proteins and nucleic acids, and these are not the just ones that we have. You will be seeing, as I told you, many and many examples in organic and inorganic chemistry where we will be having hydrogen bonding. Okay. So these hydrogen bonds, they do influence the structures and the properties of many compounds. The strength of the intermolecular hydrogen bond, how strong this bond is, this will be determined by the Coulombic interaction between the lone pair of electrons of the electronegative atom. So fluorine, this has lone pair of electrons, right? So this lone pair of electrons, these will be attracted by the hydrogen atom of the other molecule because this is having a high partial positive charge. This is not a complete charge, but the partial positive charge is going to be also quite high over here. So this is going to, there is going to be an attractive force over here, and the strength of the interactive force, intermolecular hydrogen bond, this will be depending upon the interaction between the electronegative atom of one molecule and the hydrogen atom of the other molecule. Right? So as I told you, we will be discussing a lot about this in the next lecture, which is a complete lecture on hydrogen bonding. Now, after we have done the attractive forces, all of them, let us understand what are repulsive forces. So as I told you, when the molecules, they are going to come close to each other, they will be experiencing not only attractive forces, but they will be also experiencing repulsive forces. Why? Well, when two molecules, they are going to be brought together, you will be seeing that the electron clouds of both the molecules, they are going to come closer together, and the electron cloud both are going to be negatively charged. So the negative charges, they are going to repel each other. So this is one type of repulsions that we will be seeing. The other type of repulsions between the nuclei of the two molecules. So the nuclei, they are going to be positively charged. So when the two molecules, they are going to come closer to each other, the nuclei and the nuclei of the two molecules, they will be repelling. The electron clouds of the two molecules, they will be repelling. Now, what is the importance of this repulsive force also? There is a very delicate balance between the attractive and the repulsive forces in the various molecules when we have the three states of matter, the solids, the liquids, and the gases, right? So in the solids and the liquids, the molecules, they are quite close to each other. So when they are quite close to each other, the repulsive forces are also going to be of a higher magnitude. And when they are going to be of a high magnitude, there is a very delicate balance between the attractive and the repulsive forces. If you try to compress the liquids and the solids, they are going to be very hard to compress. Why? Because if you try to bring the already quite close molecules together, the repulsive forces, they will be increasing beyond the attractive forces, right? And when you are going to try to compress them, you will not be able to compress them, right? So the liquids and the solids, they are hard to compress because of the presence of these repulsive forces. And in these states, the molecules, they are already in close contact, so you can understand that they are going to resist compression, and that would result in the increase of repulsive forces. So please do remember this. The gases, they can be compressed. The molecules, they are far away from each other. We can bring them together. Okay, so that would be causing an increase in the attractive forces more than the increase in the repulsive forces. So the gas molecules, they come together, but whereas the liquids and solids, the molecules are already quite close. The repulsive forces, if they are going to increase, well, this is not going to be possible. And that is very easy for you to understand with one example also, that if we have water in a glass, if you put pressure on it, keep on putting pressure on it, can you convert it into ice? No, you cannot. Why we can convert it into ice? How is it possible? That is again something that we will be discussing in the coming up lectures, which are going to be very interesting. And I hope now you can understand why we are studying, why are we paying so much focus on these intermolecular forces? Because these are the ones which are governing quite a lot about these three states of matters, the solids, the liquids, and the gases. So that would be all for this lecture. As I told you, the next lecture is going to be a detailed lecture on hydrogen bonding. So please be with me for that lecture. And for that, what you have to do is simply, if you've not subscribed to the channel till now, please do that and click on the bell icon as well. The moment you do that, whenever we are going to put up the next lecture, you would be getting a notification and then you can watch the lecture. If you have any doubts, feel free. You can mail us at h2ochemistry@gmail.com. You can join us on Facebook page of the channel that is by the same name of H2O Chemistry, and also you can put your doubts in the comment section, but please do not keep them to yourself. If you want to excel, just clarify your doubts and we are there to help you all. And if you've liked the lecture, before leaving, one last request, please do click on the like link. This really motivates us to prepare more lectures for you. Thank you and have a nice day. God bless you.